Hello students, so we are back for our next class, which is again module 3. The chapter 2 is dielectric. I am Dr. Shubhankar Chakraborty. Okay, so let's start the class. Okay, so first thing is, what is dielectric? Okay, so a dielectric is basically nothing but a insulator. Okay, dielectric material means an insulating material in which electrons are tightly bound. Okay, so dielectric is an insulating material in which electrons are tightly bound. That means basically this is an insulator and there are no free electron for the, so no free electrons are there to conduct. Now the question is that then why we need to tell that this is a dielectric, it is not insulator. So there is some very basic difference between dielectric and insulator, and that is why two different names are given to them. Okay, so the basic difference between the dielectric and insulator is that in insulator doesn't allow charge to flow through them. Okay, so in insulator you cannot have any, by any means insulator cannot allow, it does not allow charge to flow. Now you can ask me then why dielectrics are insulator but they are not doing it. But for dielectric what happens is that dielectric allow charges to flow only under a very special condition. Subject to an external electric field, which is actually, we'll come to this in detail how it is doing. Okay, we'll be discussing that how this actually doing. It is not the normal electric flow that we generally understand, it is something different. Okay, uh, then what is the utility of dielectric? Why we use dielectric? Probably you know that dielectric materials are used in case of capacitor. Okay, for a, let us denote what is dielectric constant first, then. Okay, so we need to know dielectric constant, that is actually quantitative measurement of how good a dielectric is. Okay, so for any capacitor, we know for a parallel plate capacitor, the capacitance is denoted by epsilon 0 A by D. If this is my capacitance, and this, if this is vacuum, then the permittivity is epsilon 0. Okay, now if we replace this in between the space between the two parallel plate with some material. Okay, let us say we have put some material, okay, which is actually a dielectric material, then for the same capacitor with a dielectric, the capacitance become epsilon A by D. Then then this permittivity is changed to epsilon. Okay, so therefore the dielectric constant can be defined as It is denoted by K, which is nothing but the ratio of the capacitance with the dielectric by ratio of the capacitance without the dielectric, which is essentially epsilon by epsilon 0, which is epsilon r. Therefore, dielectric constant, we can write it as it is equal to relative permittivity. Okay, so we got a relation where we have K equal to epsilon by epsilon 0, which is equal to epsilon r, and this capacitance C is K times C0, and this is the reason that why we use dielectric material. So if we place a dielectric material in between a parallel plate capacitor, then we can have a capacitance whose capacitance is increased by K times. Generally, the value of K is integer and it is greater than 1. For water, for example, it is around 80. Okay, for glass, wood, it is something between 10-20 of the order. So 10 times or 20 times you can increase it. Okay, let us now come to the second part of it, which is called the polarization. And remember that this polarization is not the polarization that we have discussed in case of optics. In case of optics, it is the polarization means the electric field, optical vector or electric vector, and here it is, when I say polarization, this is the polarization of electrons or polarization of dielectric. Okay, so what happens is that the process of creating dipoles or inducing dipoles in a dielectric material by an, so this is what is polarization. Polarization is the process of creating or inducing dipoles in a dielectric material by an external electric field. What do we mean by that? Okay, so what happens is that we can have some material, okay, where we know generally what happens for a material is that at the center we have a nucleus which is positively charged and electrons are orbiting around that. Even if the electrons are orbiting around that, but the center of the electron is generally the center of the nucleus. So it may happen that center of the electron and center of the positive charge and negative charge are at the same point. Okay, so and another point can be where the center of positive charge, this may be the center of positive charge, and this may be the center of the negative charge. They are shifted by some amount. Okay, so we can have one point where I have both positive and negative charge at same point. I can have one issues where I have this. So if same charge, so if this is plus q, this is minus q, they are separated by a very small distance, then this is known as a dipole because there are two poles. This is just like the magnetic dipoles we are having. Okay, so we can have two type of dielectric based on this. One is called non-polar dielectric. Okay, and another is called polar dielectric. What is non-polar dielectric? Non-polar dielectric means a dielectric material in which there is no permanent dipole exists. So there is no permanent dipole, and here obviously there is permanent dipole. Now what happens is that, so basically this is my non-polar dielectric and this is my polar dielectric. So I have not used any external electric field still, but they have already have dipole. Here I don't have. Okay, so basically center of gravity of positive and negative charges are same, and here center of gravity of positive and negative charges are different. I can give you some example. For example, the non-polar are O2, H2, N2. Here I have HCl, H2O. These are the cases. Now what happens if we apply electric field to that? Okay, now what happens is that if I apply an electric field in this direction, okay, if I apply an electric field, okay, then what happens is that electric field is, we know electric field starts from positive and then go towards negative. So obviously what happens is that positive charges will move in this direction and negative charge will move toward that direction. So this will be deformed and this may take a shape like this, and the center of the positive and negative charges are shifted. So this positive charge come here, negative charge come there. Okay, so this become polar dielectric by inducing. So I am inducing a dipole here. So this is the process called polarization. Now the question is, if I apply electric field in the polar dielectric, which is already a polar, then what will happen? So in this case, the dipole, the distance between the pole will increase or decrease depending on the direction of the electric field. So the distance between them will increase or decrease. Okay, so basically by applying electric field, we can induce dipole moment in the non-polar material, and we can increase or decrease the dipole moment in case of polar dielectric. Okay, so let us now consider how to measure this polarization case. Okay, so for this case we have to know something called polarization vector. Okay, so if I have a positive charge here, I have a negative charge there. So it is plus q, it is minus q, and the distance between them is d, where d is very, very less. Okay, d is very, very less than the point where we are measuring that. Okay, so the dipole moment, that is, we denote it dipole moment mu, which is a vector, which is I denoted by qd. In some book you will see they written it small p equal to q into d. We are not using the small p here because we will be using polarization vector as my capital P, and that is why we are not using this. We are using mu. Okay, so polarization vector is defined as the, so let us now discuss this polarization vector. It is defined as the induced dipole moment per unit volume Now if capital N is the capital N equal to number of molecules per unit volume, then the polarization vector I can write it as P equal to N into mu. Okay, or generally without vector notation I can write it P equal to N mu. It is capital P, remember that it is capital P. Now let us consider another case where, now if a dielectric slab, if I have a dielectric slab of thickness D and volume V. Okay, so basically this is my capacitor, this is the dielectric. Okay, this has a distance thickness D, volume is V. Okay, between two plates of a capacitor. Then what is the dipole moment here? I have one charge here, one charge here. So if I have Q here minus Q here, so distance between them is D. So my dipole moment will be Q into D. And the polarization vector is given by capital P is equal to QD, that is the dipole moment per unit volume. So the definition is polarization vector is induced dipole moment per unit volume. So dipole moment I get this. So this is my dipole moment Q into D divided by the volume V. So this is my, by definition I got that. So this is QD. Now volume is nothing but area into displacement, area into the distance. So basically this is Q by A. Now Q by A is nothing but charge per unit area. Now charge per unit area, we can call it a surface charge density. So we can denote it by sigma. We will be writing it sigma P because this is due to the polarization. So this charge is due to the polarization. I'll come to the process of polarization in the next topic. But there can be in some metal, in capacitor, there can be some charges which are free charges. So for that case, that will be sigma if I have some external charge. So this is called surface charge density. Okay. So I can say that polarization is also equal to surface charge density. Then we have to know something called susceptibility. It is called susceptibility. So susceptibility, it is denoted by chi. So this is not X, this is some bend. So this is called chi. We write it E so that it is electric, because there is something called susceptibility in magnetism also. So just to differentiate between them, we will write it chi E. In case of magnetism, I will be writing chi M. So this polarization or this strength of polarization, okay, is directly proportional to, this is directly proportional to applied electric field. This is proportional to applied electric field. Okay, so basically we can write this P, this is proportional to E, or we can write P equal to epsilon 0 chi E into E. Okay, so susceptibility can be written as chi equal to P divided by epsilon 0 into E. Sorry, I am not using the vector sign here. You can put the vector sign. So it is the ratio of the polarization to the net electric field. Okay, so this epsilon 0 E is the net electric field. Why it is called net electric field? Because if you have some material here, instead of epsilon 0, if you have some material here and we have some electric field outside is E, so electric field here inside will be epsilon into E. Okay, so that is why it is called the net electric field. Now we are coming to the most important part of this chapter, the relation between dielectric constant and displacement current and electric field and also susceptibility. Okay, so what happens? Let us first try to understand how the polarization happens, and that is the fundamental thing we have to understand before we start. So I have a dielectric material. Okay, I have a capacitance with where I have a dielectric medium. Let us say I have a dielectric medium in between this. So what happens is that in capacitor, in one plate I have all the positive charges, in another plate I have all the negative charges. Okay, so this is plus sigma, this is minus sigma. Okay, so I have a external electric field E. Let us write the external electric field E here. Okay, now what happens is that there is a negative charge, so all the charges within the dielectric will be aligned. How? There will be the negative charge, then there will be positive charge, then there is negative charge, then there is positive charge, then there is negative, then there is, so like this it will be arranged due to the induction. Okay, now what happens is that ultimately this is like a, this is one dipole, this is like another dipole, this is like another dipole, so they are actually, they are a tiny dipole, they are arranging in the same direction. It is actually the in the opposite direction to the applied electric field. So what happens is that essentially, okay, this and this will cancel, so finally we can have a situation where I have these positive charges, I have the negative charges here. So this is plus sigma, this is minus sigma, then I have a negative charge here due to the polarization. This process is called polarization. Okay, you cannot see this in any insulator, only in dielectric you can see. So there is a inbuilt electric field from this positive charge to negative charge, and this is actually very important. Okay, so this is, we call it EP, electric field due to the polarization. I have an external field which is E, and you see they are opposite to each other. So this process is called polarization. Okay, and due by this process of polarization, so induced dipole moment are creating, and due to that there is an polarization electric field. So let us call it E0, external electric field. So external electric field E0 is sigma by epsilon 0. You can ask me how we have got that. For this you have to go back to the idea of your class 11, where you have calculated the electric field due to a thin sheet of paper. If I have a, in two-dimensional paper I have the charge distribution in one plate. If it is having one surface, then it is sigma by epsilon naught. If it is having two surface, then we have sigma by 2 epsilon 0, something like that we have done by taking the Gaussian surface and all. Please go back to your class 11 idea and you can directly put this. Okay, now due to the presence of electric field, due to the presence of dielectric material, due to the presence of dielectric material, my electric field, net electric field is reduced and it is becoming E0 minus EP. So E0 is this, EP is on the negative side, so net electric field I will having E. So E is nothing but E0 minus EP. And E0 I have sigma by epsilon 0, minus EP is nothing but sigma P by epsilon 0. We have done that. So sigma P is the this is the polarization due to the this charge distribution. This is the sigma, this is the external one. You can call this as sigma P, this as sigma P, the initial internal one. Okay, so you can write it 1 by epsilon 0 sigma minus sigma P. So epsilon 0 E is nothing but sigma minus sigma P, which is sigma minus P. I can write sigma P equal to P because we have done that in the previous case. We have seen that P equal to, I can show that P equal to sigma P. So that is what we are using here. We can write that P equal to sigma, instead of sigma P, I can put it P. So I can put sigma equal to epsilon 0 E plus P, okay? And by Gauss's law, so we can show, I'll come to that, we can show that displacement current D equal to sigma, electric displacement vector D equal to sigma, we can show, I'll come to that, I'll prove this. So therefore we can write displacement vector D equal to epsilon 0 E plus P. This is a very, very important proof, okay? So please check that. Now we have P equal to epsilon 0 chi E into E. We already have that, we have proved that. And also we have generally D is epsilon E. We have used this in the Maxwell's equation also. Go back to your class notes and check. Okay, so we can put this together here. So therefore we can write epsilon 0 epsilon R E is equal to epsilon 0 E plus epsilon 0 chi E into E. So that means epsilon R equal to 1 plus chi E. That is another relation. Okay. So this proof is also important. Then there is something called polarizability, the details of which I'll be not discussing. I'll give some understanding of it. Okay. So dipole moment induced dipole moment is directly proportional to the applied electric field. Okay, therefore mu actually proportional to E. We can write mu equal to alpha into E. This alpha is called the polarizability. So this is actually induced dipole moment per unit. So it is called induced dipole moment per unit electric field. Okay, the unit is this. Okay, there are generally three types of polarizations are there. Okay, number one is electronic polarization. Number two is ionic polarization, and number three is orientational polarization. What happens in all the cases is in electronic polarization, what happens is this, due to the shifting of electrons, the polarization happens. That means the positive and negative charge actually shifts due to the applied electric field, or they have the permanent dipole moment. For ionic polarization, it is can be seen in case of some ionic material, okay, like sodium chloride or all. So they have, due to the ion presence there, you have the polarization. Orientational polarization means they have already permanent dipole, but they are randomly oriented. If you apply some electric field, so they will be aligned in the direction of the electric field, and that is called orientational polarization. There are some discussion and detailed you can find in textbook. I'm not sure how much it is required, so let us, for the time being, let us only stop here. But if needed, we'll be discussing in the class, or maybe I can make another video. Okay. The last topic in our syllabus is Clausius-Mossetti relation. Now the point is that this Clausius-Mossetti relation Clausius-Mossetti equation. Now this equation, the deduction is not there in our syllabus. We don't need to know the, only we need to know the equation. Okay, and basically this equation we need for MCQ type of question. Okay, for cubic symmetric crystal. Okay, this equation gives the relation between this polarizability and the dielectric constant. So I can write k minus 1 by k plus 1. So k min, let us write it again, k minus 1 by k plus 1. So it is dipole moment, sorry, dielectric constant. This is equal to n alpha by 3 epsilon 0. You only have to remember this. That is all what we have. But before I finish, let us give you some idea about the displacement current, which I have not given you. Okay, so let us say I have a circuit, okay, where only a capacitor is connected. So let us say a current is flowing. I see there is this, the area is A, the distance between them is D, and this is V. So here I can write the current I equal to, I know this is dq dt. So what is the charge here? Q is C into V. So C is a constant. So this is dV dt. Okay. Now this C is nothing but epsilon 0 A by D. So I have I is epsilon 0 A by D dV dt. Okay. Now electric field with potential V is, E is, you know that, probably you know this equation, E equal to minus dV dx, or we have done E equal to grad V. So dV dx gives me the electric field, so voltage divided by the distance between them. So therefore I can write I is equal to epsilon 0 A. Here I have dV dt, dV dt is dV dt, so V is E into D, so it is D cancel out, so I'll be writing it dE dt. So I can write I by A. I by A is nothing but the current density. So current density is epsilon 0 dE dt. Okay. So I have a current density. This is not the normal current density because this is not a conduction current. Okay. This is basically a displacement current that is flowing through the circuit. So this is JD. This is equal to d dt of epsilon 0 E. Okay. So this is called del D del T, and D is nothing but epsilon 0 E. In vector notation you can write it this. This is known as electric displacement or displacement vector. This same vector was used in Maxwell's equation. Okay. So JD equal to del D del T is the displacement current density. So this is called displacement current density. Okay. So thank you. That is what we all have in our dielectric chapter. Hope you will be going through the notes and answer the assignment question. Thank you.